be sure to properly orient the Tuco camera once I actually see the little critter. I think he might be taking a nap upstairs. Let's see, how's our audio doing? Check. Cool. Oh, good afternoon, everyone. Let's see if I can actually switch this channel. Hi. Alright, so yet again, a few more changes to the streaming setup, but hopefully I've got most of the glitches worked out. I think I should be saving some CPU and also maybe being able to stream some more HDMI doodads. I stuck a third HDMI grabber on this machine. The other two are Thunderbolt, but this one's USB 3. And it seems to be alright so far. So, let's have a little bit of context. Since it's always nice to have, for some of you who might not be familiar with the kind of overall way that I do these videos, it's partially, I think the streaming itself is a nice, it's a nice kind of collaborative environment. It's like nice to work on stuff with other people, kind of virtually hanging out with you. So I like kind of creating and watching these streams for that reason. But I also tend to use these as an opportunity to collect also, in addition to the footage I'm streaming in 720p, I've also got higher quality recorders that I use to get videos, or to get video for these kind of more meticulously edited videos that I eventually release when I finally finish them. And then I try to have as much overlap as possible between the different videos I'm making and the different projects I'm working on. And so this project has some aspects that are that I'm going to be documenting in different videos about both this kind of glitching setup I'm working on and the kind of circuit fabrication techniques involved. And so yesterday there was a stream where I built this little adapter to help me. This is a development board that I'm doing an experiment on where I'm trying to extract its firmware by contacting its HTTP server and then glitching it at just the right time so that I can corrupt some of the internal data values inside the HTTP server's file lookup code so that it's actually reading some other part of the flash memory instead of like index.html. And I want to try to use that to extract the firmware from this chip. And if it works on this chip, then I can apply it to other devices that use the same microcontroller. So, I had a lot of this setup working pretty well in terms of being able to reproducibly trigger this. I'm using this Raspberry Pi with an external Ethernet adapter to actually do an HTTP GET, and then I'm using this chip whisperer board to actually do some analog acquisition to look at the chip's power rails and get a closer look at what it's doing. It's also generating the clock for this whole setup, so its samples are synchronized to that generated clock, which keeps things nice and synchronous. You don't have to have quite as high a sample rate that way. And then I've also got this FPGA in the middle that I also talked about on an earlier stream that's doing some clock management. And actually, one of the things I wanted to start with is since I wanted to both explain it on this stream and have some reference material for later when I put this into video, I made a little diagram about the clock situation going on here. So let me make sure this camera is going, and then we can get that on actual video. Yeah, format. I just tend to format these cards right before I use them. Alright. There's another view of this Rube Goldberg machine. I actually tidied it up a bit since it was on camera last, so maybe I'll get another view. Alright. So yeah, we've got this front thing is an original Raspberry Pi in a rainbow case, and this board on top is an external Ethernet adapter that it's actually 10 base T and attaches over an SPI bus. And by underclocking both that Ethernet chip and the SPI bus attached to it, we can interface this artificially slowed down version of Ethernet to the outside world. Then I've got this tiny, tiny cable going over here. And then that board on top is the thing that I made on yesterday's stream. So it's got those two little tiny chips, and those are buffers. The first one is just kind of cleaning up this not so great clock or trigger signal that I'm getting from the FPGA over this big wire. And then the second one is amplifying that up to 5 volts and then using that as a gate drive signal for that big MOSFET, which is then kind of draining the 1.2 volt core voltage rail of that microcontroller under there, which is a little bit too close. Let's anchor this camera. I keep trying to manual focus, but it's still in servo AF mode. All right, let's point. Great, so this little board on top is the thing that we milled yesterday. This is a MOSFET, and it's a super simple board, just much easier than fly wiring everything together. And then this test point down here that's also wired up to these SMA connectors here, that is the microcontroller's 1.2 volt core voltage rail, which you can also find on the other side of these little capacitors down here, which is just the minimum amount of capacitance I had to add in order to help the regulator that's built into this microcontroller stay stable. So it's under what the datasheet recommends, but it's enough that it doesn't oscillate. And then so the goal is to have really short wires here, low resistance, low inductance, a MOSFET that when it's turned on fully is very low resistance and can, if you drive it fast enough, can turn on pretty fast. But this MOSFET is going to just kind of suck all the energy out of this transistor and out of the chip itself. And then when I switch this off, it'll then end up causing kind of a ringing rebound as the voltage regulator then tries to stabilize. Because from the regulator's perspective, it's getting this huge increase in current. So it starts to adjust for a higher load. But then when the load disappears, it kind of overshoots. And then you can also get similar effects due to inductances in the system, which probably isn't an issue here with things being so small. But yeah, I'm causing somewhat localized havoc on the power supply, and I'm still tuning it to try to figure out what kinds of pulses make the most, I'm still looking for a way to glitch this particular processor that causes it to, compute incorrectly without just crashing or without just continuing. And so that's the stage of this I'm on right now. I've got a test setup which is, becoming more stable, but and I've got some visibility into the operations going on by looking at the power consumption on that vCore rail. And I can see there that even though there's still some noise I haven't gotten rid of yet, I can also see a stable pattern that indicates that the CPU is executing the same way every time I trigger the experiment. So this is a good, important feedback signal. And I can also get some of that from an oscilloscope too. The Chip Whisperer A to D is really just basically like a built-in oscilloscope that has some kind of synchronicity advantages sometimes. And then over here, these two wires are for the 3.3 volt and 5 volt supplies for these two buffers. So I can do the gate drive off of 5 volts. And then some extra stuff in case I needed it. So some test points for the inputs and outputs. And right now I've got these two buffers on this chip paralleled together, which I wasn't sure if that would be a good idea. Like I wasn't sure if it would make it faster, so I made these extra wide in case I needed to cut them. So anyway, this it's not optimal. So these little buffers are not nearly good enough in terms of peak current to really charge up this MOSFET, because this thing is just a big capacitor, like the gate. So in a MOSFET, the gate is electrically insulated, but it's still this large area, which is then, hovering over this ground plane, basically. So you have to charge this like you would charge a capacitor, because physically that's what it's become. And these little chips, they're not even like rated for instantaneous current, because that's not what they're designed for. They're like logic buffers that are designed for, I think, like 35 milliamps continuous. And I think somebody in the chat last time was nice enough to actually do the calculation that to get the kind of tens of nanosecond rise times that I'm looking for with this particular MOSFET, then it would probably take, like an amp of peak current. So I'll likely do another revision of this with a real MOSFET gate driver in the near future, because it would be nice to improve it. But from my testing so far, this is actually a big improvement over the previous setup where I was using the glitching transistor built into the chip whisperer. And so I'm getting various non-ideal waveforms at these two buffers, and I think I can demonstrate those in a sec. I don't have glitching enabled right now, but it's easy to turn back on. So we'll take a look at those waveforms. But basically, the signal coming from the chip whisperer is still kind of loaded down by a lot of capacitance from its onboard MOSFET. So it's got kind of this slow rise time, and so when you take that square wave and then filter it through with this slow capacitive rise, and then you're kind of sending that over a wire, and then basically when that reaches a threshold, that slow rise then triggers this first inverter to flip. So you see that slow rise, and then somewhere over here, it'll actually flip pretty fast. But what we've done now is you've dramatically shortened the width of your pulses. So that's actually reaching some annoying limits here. And so one solution, I can turn the pulse width up to almost 50% of in this case, the 30 megahertz clock, and I can get pulses through that actually manage to turn this MOSFET completely on for enough time to, bring V-core all the way down to 0 volts and cause it to ring nicely when it comes back up, and so that's nice. But in order to get that to happen at all, I have to give it such a wide pulse that now I don't really have a lot of control over the actual pulse width. So that's not really optimal either. So one way to solve that is to build a better circuit here. But I think maybe the simplest solution at this point is to just underclock the entire system even more. Because I haven't actually looked, I hadn't, until preparing for this particular video, looked into hadn't looked in here until this particular stream, this particular step, whatever we're on. I don't exactly know how I'm going to edit this together. But yeah, before this particular step, I hadn't really looked into what the limits were on how deep I could underclock the system. So this system on a chip under here, it normally runs at 25 megahertz, but that's just the input clock. That's the 25 megahertz crystal that drives the Ethernet controller directly, but the actual CPU has a clock frequency of 120 megahertz. So there's an internal phase-locked loop that actually multiplies the clock up to a really high frequency and then divides it again to do this kind of fractional clock synthesis. So that actually is kind of annoying, because if the chip whisperer is dealing with just that external clock, not only is it way slower than the CPU is actually dealing with, so I don't have a lot of visibility into the cycle level timings, it's not even an integer multiple of the actual CPU clock. So that's part of why the first few experiments I did on this, it looked really bad. Like, I could tell it looked kind of stable, but there were kind of beat frequency-like patterns all over the place where, I would get something that looked kind of nice, like something kind of CPU activity-like, but then it would almost have like a sinusoidal envelope to it as it, as those kind of lower frequencies from the, weird multiple made it just really annoying to deal with. So it would be great if, first of all, the chip whisperer is dealing with pretty close to the same clock that the actual, not the external crystal is, but the actual core microcontroller is using. And it would also be nice if that was just slower, so that I didn't have to deal with capturing a signal at, ideally I want to capture at 4x the CPU clock. So I don't really want to have to deal with 480 megahertz of analog bandwidth, because that's a lot of money, and I don't have equipment specified to that right now, and it would be really nice if I just didn't have to go there. And then it would also just be, it would make this glitching setup easier, because now I don't have to turn the MOSFET on quite as fast. I can just kind of slide past some of these non-ideal aspects of the current setup. I'll still probably want to improve the MOSFET, but this I think will be an improvement in many ways. So for that reason, I really want to know, I should avoid snapping while I'm talking. Should also make sure to drink water. I'm surprised the cat isn't hanging out by the heater again. All right. So yeah, I'd only recently looked into why, what the actual limits are as far as how slow you can turn down the clock. And the main suspects are the phase-locked loop that's actually doing the multiplication, because those usually have a narrow window of clock frequencies where they're stable, and if you get outside that, then they might work, they might not, they might work if you reset them enough, or they might just oscillate at the wrong frequency, or they might jitter a whole bunch. They can just behave really badly. So it could be something like that, or it could be something, the other kind of major culprit would be the Ethernet. So, in the early tests I was doing, I wasn't really sure whether the CPU wasn't running or whether I just couldn't talk to it. So narrowing those down actually tells me that I can run the CPU at much lower frequencies than what I was able to talk to it at. So I think from my testing so far, I was seeing that with that 25 megahertz crystal underclocked down to like 5 or 6 megahertz, I think it was fine at like 5 megahertz. And I was able to ping it. It loads the web page. It might be losing packets every so often, but it seems to mostly be fine. But if I clocked it down even further, it's it just wouldn't respond, and it was difficult to diagnose why. Since not only am I dealing with a device not responding to pings, but this is a lower level of failure, so it's more like the Ethernet interface doesn't detect that the link is there. And is that because there's a timing issue in the link detection pulses, or an electrical issue in the pulses getting there, or is the Ethernet controller just crashed because of some clock going too slow for it? And the other issue I had to verify was making sure that even though I'm underclocking the Ethernet controller so much that both it's alive and the Raspberry Pi can keep talking to it, which means that the SPI traffic has to be probably substantially slower than the underclock I'm giving to the Ethernet controller. I think in the data sheet, so it normally runs off of 25 megahertz, and I think the maximum SPI frequency is typically like 10 megahertz. So, assume it's designed. Well, you have to make some assumptions because you don't know why it's 10 megahertz. You don't know whether that's because there's something in the silicon routing that can only handle 10 megahertz, or you don't know whether there's something where it needs a little more than 2 clock cycles to handle something per every SPI clock cycle. It's usually the latter when it speeds this slow, because usually the kind of silicon propagation delay issues are only an issue with, like hundreds of megahertz kind of things, or at least like many tens, not just like 10. So I suspected that as you scale down the input frequency to that ENC28J60 chip, that you'd also need to scale down the maximum permitted SPI clock frequency. And then it wasn't clear what the minimum clock frequency that the Raspberry Pi can even tolerate is. I think I tried setting it to something really low, like 50 kilohertz, and it seemed like it had just crashed. But right now I'm running it at, I think, 100 kilohertz, and it's slow, but it's working. So I've got a diagram. Let's go to the diagram. Oh, somebody's asking me if I'm trying to dump the same firmware for something in my day job on a different, like something on the same microcontroller. And yeah, I thought that was clear. That's what this is something I'm doing that I like making things overlap whenever I can, and so this is something that I'm doing because it's something I need to for my day job, but then it's also something that I can share, and it's something that I would like to include in my videos in the future. So, this made sense, and so they know I'm streaming stuff and they're fine with it, and we're all on pretty much the same page as far as like wanting this information to be more accessible. So, okay, how visible is this? So this is pretty simplified. These PLLs are phase-locked loops, or effectively clock multiplier / divider units. And they're actually a lot more complicated than just one step that multiplies by a number, but that's what I'm drawing them as here. And the device under test here is a system on a chip that includes a CPU and an Ethernet controller. Those are the main things we're interested in, at least. And the Ethernet controller is running directly off this 25 megahertz for our purposes. I think the Ethernet controller also has its own internal PLL, especially for 100 base T, but since we're dealing with 10 base T mode, I think it might even just be using the 25 megahertz directly for that. But I haven't actually had to look into that super closely. So far I've just been feeding it a different clock rate and checking out how well it copes with that. So both of these Ethernet controllers, since it's a convenient rate with the way the specification's designed, they expect 25 megahertz. So in the normal configuration, the one in the system on a chip gets it from externally from this crystal. And the peer that I'm talking to over the Ethernet twisted pairs, it's also going to have a 25 megahertz crystal. And then, excuse me, should stay hydrated. All right. So the system on a chip, in addition to the Ethernet controller, has this CPU. The CPU runs at 120 megahertz normally, and that's a PLL that's configurable in software, but for the cases we care about, the recommended configuration that TI has for this chip and the configuration that all the examples seem to use, the CPU is running at 120 megahertz with an effective multiplication of 4.8 from this PLL. So it'd be really nice if we could have the chip whisperer working off of a clock more like that. And maybe this clock rate is kind of messy, but then at least the clock that all of our analysis tools are working at doesn't have this weird 4.8 multiplication factor relative to the clock the CPU is running from. So my solution there was to take off these crystals and wire these directly up to this PLL, which is doing the inverse operation. So I have the FPGA in the chip whisperer synthesizing whatever clock I want, a faster clock that is going to end up matching the CPU clock. And then it's divided by this PLL, then multiplied again by this PLL, and then we theoretically get something that matches. So for some examples of what rates this could mean, the normal rate has this orange line, this clock running at 120 megahertz and the crystal at 25 megahertz. The rate that I've been using successfully so far, I've got the chip whisperer generating a 30 megahertz clock, and this intermediate frequency out here that's replacing the crystal is 6.25 megahertz. So that works, and I'll demo that in a sec. It's actually, I've still got a ping going that I can just switch to on the computer. And that setup works, but it's still a little bit fast to be really friendly to deal with. And this particular glitching board is not quite fast enough to give me a useful pulse. And just in general, a lot of these tools are hitting their limits at, like I could make a new version of that glitching board with a proper MOSFET driver, for example. But from what I'm seeing so far, it looks like there's on about the same order of magnitude as of that problem, I'm having a problem with just propagating that signal from the FPGA to the glitching board. So it would just make the setup easier if I didn't have to worry or deal with such high frequency signals or such rapid pulse edges. So I'd like to make this easier to the extent that I can, and underclocking is certainly a way to make that happen. And there might be reasons the underclock isn't, is limited by something that we're not looking at here. So it might be limited by a watchdog timer, which could run off of an internal RC oscillator. I don't think this example that I'm working on glitching right now has a watchdog timer, but the PLC that I'm looking at that uses the same chip definitely has a watchdog timer. But often the watchdog timers are designed with such wide margins that maybe if I underclock this by a factor of 24 still, then it's still fine. But if I completely stop the clock, then in a couple seconds it resets. So that's what I'm going to try to do, is underclock it by about a factor of 24. So I want to get down into this range. I've already checked that the processor will run with this external clock at just a little over 1 megahertz and the internal clock at about 5 megahertz. And it's fine. I don't really need to go any slower than that, since I think I'm just going to risk PLL instability if I go any slower, and there isn't much of a reason to. But when I've gone below about 30 megahertz, I start to have problems with the Ethernet communications. So there could be various reasons for this. It could be the AC coupling in the Ethernet circuits here. They're sending the signals through pulse transformers, and the transformers have a particular frequency range they're good for. And as the frequency of my data gets lower and lower, then you would actually need sort of a much larger transformer to pulse to handle those lower frequency pulses. So you know, instead of trying to pick a new transformer, I would rather just remove the transformers entirely and try to DC couple these devices, which could have its own challenges. You know, I might end up wanting to capacitively couple them instead. I mean, that might be the safest. I've also thought about coupling them with some current limiting resistors, because I'm a little bit worried about DC current flowing. But I think there are a couple things we can try that mostly just entail removing the transformers from both ends and putting a breadboard in between. All right. Oh, I'm still kind of behind on chat, but I saw briefly a question about the Watchdog timer and its time base. And typically they do have their own RC oscillator, so if you underclock a device, you change the relationship between how fast the code is running and how fast the watchdog is resetting. And that could be an instant recipe for having the watchdog reset you. But often the watchdogs are designed with a lot of margin, so maybe you end up resetting the watchdog like every 10 milliseconds, but it only times out every 2 seconds. And that kind of stuff is actually pretty common. But yeah, that might be one of the limitations I discover later. And so this is a bit of a contrived test setup anyway. Like I have this processor giving me a much better trigger signal than I expect to get on the real device. But you know, some of it is so that I can validate the other aspects of the setup, like the actual glitch pulse, before kind of porting it to the other device and giving myself the harder task again. So yeah, it's mostly just trying to isolate parts of this problem to solve, and then kind of synthesizing those back into a solution for all of the problems that I end up finding. I'm gonna refill this, and I might also see if I can track down Tuco, because cat cam is so empty right now. Tuco, you wanna be on TV? Hey, Tuco. Oh, yeah. You know what? There's a warm spot for you right here. Hey, Tuco. What do you think about this spot? I know I'm sending you a heavy-handed message, but I thought you might like it anyway. You like it there? Are you thanking me or forgiving me? Can't quite tell. Okay, so while I have the DSLR out, let's take a quick look at the O-scope at this clock I'm generating, because that's something I find interesting, and I might as well get this on the recording too. So that's my 6 1/4 megahertz. I've been keeping a close eye on it because I've been having this intermittent problem where I don't know why, but something is causing something causes this to occasionally get into a state where it's just incredibly jittery, like some PLL is just spazzing out on the way. And I can't tell whether the bulk of that mess is coming from the Chip Whisperer's clock generator or my FPGA. But resetting the clock generator in the Chip Whisperer seems to fix it when it gets into that state. So, all right, let's go to the computer and take a look at what this is doing there. And to go. Okay. So I have this connected to the serial output on, I have this oscilloscope connected to the serial output on the evaluation board here, which is giving me, it prints out a little message every time the firmware starts up with like, here's my IP address, connect to me with a web browser. And I'm not going to bother actually decoding the serial message here, but what I am interested in is the timing. I want to know what speed the serial port is running at, because that tells me, A, that the processor is running at all, and that it has a stable clock. And B, it actually lets me measure what speed the processor is running at if I want to. So right now, that seems to be pretty stable, and it's running with my 6 1/4 megahertz input. And let's see, the interesting bit here is that I can see these pings coming through. The latency here is, I think, mostly at this point due to the really slow SPI clock I have set on the Raspberry Pi. The 100 kilohertz clock rate going into the ENC28J60 chip. And you don't need it to go that slow with this 30 megahertz CPU clock / 6 1/4 megahertz intermediate frequency, but it's something that seemed appropriate for the much deeper underclocks that I'm going for next, and it helps to test that in its own, without also changing a bunch of other things, Helps to test a few things at a time, a few changes. So we can also go to the web page and reload that. It's pretty slow. I think some of the initial slowness might have been DNS, because this is using MDNS to get to my Raspberry Pi, which has the proxy. But if I just use the IP address, that'll be a little more reliable. So this is working. It's slow, and we might be getting some packet loss, but it does seem all right. But we can take a look at what we're actually dealing with on the oscope. So maybe I'll get that a little closer to the camera. Oh, yeah, there was a question in the chat about the Rigol hack. I have actually hacked the firmware on my Rigol, but not to change the frequency. Yeah, I was excited about that. I knew some of the people who were involved in doing that originally, but it was, and so I kind of heard about it through their excitement. But I didn't end up needing to, because yeah, by the time I got this scope, it was like about the same price anyway. In fact, I don't even know if the other ones were available when I looked for this. For some reason, this scope was the one that seemed like the one to buy when I bought it, I assume. It's my shopping strategy. All right. always need little spools of solder handy, but then I have to be very careful where I leave them because they seem like the most likely thing to ruin my day as far as conductive debris risks go. You can tell, I mean, I complain about conductive debris a lot. It's something I worry about. There we go. Hey, Cat. How's your morning / evening? Oh, Cat's gonna do some self-cleaning. Oh boy. Okay, so these clock signals are not the cleanest looking square waves, but they are totally serviceable. That's the 6 1/4. What I'm actually interested in, though, at this point is the Ethernet signal. So let's keep that, since when we're looking at other signals, it's always nice, you know, like besides just keeping an eye on the clock, having the clock on the scope lets us see that the other signals are synchronized with it, which is always nice. Let's see, that probe is for the slow scope. This probe is for the Ethernet. So, yeah. This is where I would really like a little Ethernet interposer tap thing. I've actually got a blank circuit board for one of Michael Osman's Throwing Star LAN taps, which would have been almost perfect for this, but then I just didn't have the right style RJ45 jacks handy to just assemble it right away. Yeah, I think I'm just gonna cut into this Ethernet cable, because that, I think, is much easier than trying to get in there. So let's do that. I already made a single-ended version of that, like, I just crimped one of these. We might do that soon, but I suspect that I'm just gonna end up pulling this entire, oh, it's a little bit off frame, but I suspect I'm just going to end up pulling this entire jack off of this circuit board, since it's, I want to take off the transformer, and this is unfortunately one of those tidy little modules with the integrated transformer. So let's just see if we can cut into this without damaging it too much and get at the signals we want. So luckily this is just 10 base T, which is a lot easier to take a look at electrically. You know, 1000 base T, which is pretty common now, uses all the wires. But 10 and 100 only end up using, at least if you're following the standard that these are using, they use the orange and the green wires for transmit and receive. And a lot of adapters, I think in this case, the one on this board has automatic detection for which one is transmit and which one's receive, so you don't need a specifically crossover cable in order to connect two devices to each other. orange and green. The other thing that's tricky about this is I can't just like jab the scope probe on the transformer there and measure it, because this little connection between the two machines is usually not referenced to any one particular ground. So, you know, if you just stick your scope probe there, there's nothing to complete the circuit necessarily. So nothing's going to actually, you know, no current will flow into your scope probe to charge it up to a voltage which reflects the signal that's at the transformer there. You know, you don't have any kind of useful reference to measure it relative to. Oh, you know, I think I have a doodad that'll help with stripping this. All right. I also feel like a total idiot every time I have to put one of these RJ45 crimps on a network cable. Because I feel like, I don't know, I just don't see how there's a good way to do it. Maybe I just need to watch some YouTube videos of pros doing it, but I always feel like I'm just like fiddling with it to get all the wires like lined up just right, and then I put the connector on, and then I check it, and inadvertently, like, you know, one of them will be swapped, and I have to redo it. It just always feels like a mess. I think I can use this stripper to, whoops, well, maybe it cut the wire. Maybe I'll just twist it back together. Oh well. I think I'm going to solder that too. That was going to be so easy, but it was too violent. I guess I need to turn down the violence knob on this thing. Can't quite see him there. You clearly need the Tuco robot. Actually, before I put Tuco Cam on this tiny tripod, I had it on like a clamp, so I could just like put it on whatever furniture Tuco was sitting on, which seemed okay. It just wasn't great when we wanted to play games together. The tripod is easier to do that with. Yeah, that kind of, all right. A little too aggressive for this wire with that particular setting. I would recommend using slightly more care if you're trying to splice into the wires in somebody's like top secret computer or network or something. There are actually really nice ways to do that. I forget where I saw this, but I saw a pretty nice talk on a, it was like a combination of like a physical, like splicing method that was pretty interesting, and like a bit of active hardware. I forget what it was called, but I think there was like a Black Hat or a DEF CON talk on it. And so the idea is this is like a doodad that you can, like if you have a cable sitting in front of you and you just want like into that cable, then ideally what you want is to put like a little Ethernet switch in there, or like some active device that can very quickly log and possibly modify traffic as it goes across there. But ideally you also just don't even want to break the connection, you don't want to be noticed. So I think this was something where you could like physically punch the cable down into this thing that it would make contact to all the wires like on both ends of what would then be a cut. And so you'd make all the connections, it would have relays to bridge across the cable that you were about to cut. Then you cut all the wires without, you know, shorting them together or anything. And then very quickly it would use those relays to switch between that short and the little like man-in-the-middle device that they had added. And I think it's an interesting idea. I can imagine that technique working with a lot of different protocols, you know, and that's probably like the obvious like hacker mind solution to this is like, oh yeah, obviously you can just do that with like, you know, USB or, you know, what are the kids like these days? DisplayPort or, I mean, you know, Ethernet is probably much more interesting than most other wires because that's what you have going in long distances, and that's where you have opportunities to tap into it. And so much is like just over IP now. Okay, that time I didn't cut it. That time I used sufficient but not overly terrible amounts of violence. I'm still going to reinforce them with some solder because I think I damaged them slightly in the area where I trimmed. Oh, geez, I was gonna make coffee before starting the stream, and I totally failed on that. All right, that is not pretty, but it is totally fine. Let's take a look at the signal. So this is still the working example. Very soon I'm going to underclock it even more and break it again, and then we can try to look at how it's broken and then try to fix it. So, assuming these both have transformers in them, I can just attach the ground wherever on this cable since everything is isolated electrically from the rest of the circuit. So, it looks like idle. See if I can just verify that I have data going through still. Yes, I can ping. I am sending pings right now. And we want to trigger in channel 2. Sweet. So 10 base T is nice for a number of reasons. So whereas 100 base T is you know, still relatively simple in that you've only got a single twisted pair for each direction to worry about. You still, you know, if you look at 100 base T on an oscilloscope, you just see this continuous mess, which is great if you're a 100 base T receiver, but because you've got all these edges to just keep your clock locked onto all the time. And, you know, it's not the most power efficient thing is, but Ethernet almost never is really power efficient. You know, if you look a little deeper, you see that just continuous mess is a sequence of these tokens that are, I think they're 10 bits long, and if I'm remembering right, you should totally Wikipedia this instead of just going based on my memory, but I think it's 8B10 coding, so it's like 8 bits inside of a 10-bit symbol. So it's something like that on 100 base T, and its way of signaling an idle connection, an idle but still connected connection, is to send a bunch of idle tokens. So they're not actually like real values, they're not like bytes, they're not tokens that indicate like the beginning or the end of a packet, they just indicate unused space. But if you look at them on an oscilloscope, you'll still see this like nice repeating, you know, like 10-bit waveform or whatever. So that's nice, but here we don't want that for a number of reasons. I'm trying to do terrible things to the power supply in this microcontroller, and so I want as little noise on the power supply and as little demand on the power supply as possible. So switching to a less chatty and slower protocol like 10 base T helps a lot for that. It also means that when the line isn't talking, so when we're not sending any packets, it's pretty much idle. The exception are these little pulses, and so you can actually see both going on now. Let's get a much broader view here. So this is even slower than normal 10 base T because, let's see, what is this underclocked by? This is underclocked by a factor of 4 right now. So everything you're seeing here is 1/4 the speed of standard 10 base T Ethernet. So here we're seeing these, so I forget what these are called, but I actually have the Wikipedia page for them handy because they're really interesting and relevant to this. They're like link upkeep pulses or something like that. So all of this stuff that describes like how Ethernet even knows what speed it's operating at is pretty interesting. And I found this naming convention pretty weird. It feels like an indication of how like tech-centric Wikipedia is, that this article is, it isn't called like IEEE 802.3 negotiation protocol or something like that. It's just called auto negotiation. Like that's what the word means in any context. It's this thing. So thanks, Wikipedia. First time I hit the synergy bug on this stream. Let me make sure to turn that off. All right. So, I don't know. Part of what makes this perhaps worthy of a Wikipedia article is that it's one of those things that has so much backwards compatibility legacy for it. And so you can actually see how originally there was just this very simple thing that 10 base T did, and that's the thing that I'm forgetting. Normal link pulses are what they're called, or link integrity test, I guess. Yeah, I guess both names are valid depending on what specification you're reading. So let's call them link integrity test. So when this 10 base T interface wants to know its connection is good, it does these lit pulses, and those are these little things that we're seeing on our super slow version of Ethernet. We're seeing them about every 50 milliseconds. And there's a lot more that you can get into if you look at how like auto negotiation for like, whether you're full duplex or half duplex and what speed you're talking at, and whether you're gigabit or 100 base T. So that's all an extension to this. It reminds me a lot of what they did with USB for detecting speeds, where originally there were 2 speeds, and so there was a relatively simple system with some pull-up resistors, and then they just added another speed. So they added the 480 megabits, and then had to add this kind of higher frequency pulse on top of what normally would have been their polarity detection signal. So this is interesting, but only the very first bit of this is actually relevant for us right now. If we go back to the scope, we can actually look at those signals. So occasionally we're getting a packet here, and that's from the ping. We can verify that just by changing these pings by turning them off or making them faster. So if I cancel the ping, all we're seeing are these link integrity test pulses. And already these are not looking so sharp, literally. So you can tell like this is a pretty wide pulse here, but the transformer is actually having this effect of smoothing it out. I think if we take a look at the signal coming out of the microcontroller, we'll see something much smoother. Let's just verify that. Or not smoother, but much sharper, much nicer at least. So this time I'm going to connect to the system ground and probe on the system on a chip's side of the transformer. And try to get the transmit and not the receive. And also be kind of annoyed that I put the glitching board directly on top of the transformer, which we'll have to move. I guess it's the other one. Too many probes. Yeah, I need to move this board so I can access that transformer. I can just unstick it on this side very slightly with something non-conductive. Spudgertown, population us. I maybe glued that slightly more than I... It's just hot melt, so I didn't expect it to be especially hard to remove. Okay. I can get in there with the probe just in case it's on the accessible side. I do plan on taking this off. I'm just trying to delay it until after we do this test where we want things to be on. I can still ping. I think we need to lift this board. I guess I could just hit this with the heat gun and it would probably come up pretty easily. Alternatively, this might be how I get the transformer off. Yep. Okay. Well, solved that problem slightly earlier than I expected. Let's, well, maybe I can get in there with the scope probe first before inspecting the mechanical carnage. Can at least see that signal before it's gone through the transformer. Oh, well, there's the pulse that we're getting on... Well, I don't know exactly whether that's the right... Oh, that looks like the right one. I think that might have just been some crosstalk from the transmitter. So that looks like what the driver was giving us, which is a much nicer pulse than what we were seeing. We're actually getting all the way to the bottom. It's definitely steeper on this. I mean, I was hoping to do a side-by-side comparison, which is a little harder now that I've yanked off the transformer, but that's fine. Let's just do it this way. Okay. Well, I guess the next step then, since it's hard to demo in this state, is to just solder across where this transformer used to be, and then I mean, we could do another test after that point, but I think I'm probably going to want to take the transformer off on the other side first anyway, so we can just do that while we're in the kind of soldering zone. So, I guess before we do that, it might make sense to go ahead and actually like switch the underclock down to the lower level that I'm hoping to reach. And even though we can't get any traffic through, at least then we'll be working with what we want to be working with instead of something that is still kind of too fast. So the clock is being generated by this chip whisperer setup. Let's see. I mentioned this script briefly before, but we didn't actually look at it. This is just what's setting up the chip whisperer environment. And it doesn't really kind of set up this entire experiment because I've got some of this FPGA stuff going on that it's not controlling, but everything that's actually on the chip whisperer, this is setting up. So I think we might want to get, instead of well, the numbers are all kind of weird. I think I chose 5 megahertz because it's a clean, I'm underclocking by a nice number. It's a division by 24 versus the original frequency of 120 megahertz. But it also means that with this desired frequency of 5 megahertz, this was back on this chart. At 5 megahertz, then our output frequency is pretty manageable. It's just a weird number. It's 1.04266666 repeating. So it's fine. We just have to expect a weird frequency. And so I was tempted to go up to 6 megahertz and the corresponding 1 1/4. But even though that looks cleaner over here, that means that now I'm not doing, now it's not as clean a division from the original frequency. So a lot of this is just going to look pretty similar to the examples that come with Chip Whisperer, and the main difference here is that for the target, I've got this simple HTTP module that we looked at earlier, and that's just kind of triggering the setup of the test by sending an HTTP GET instead of sending something over the serial port. Yeah, and then here's where I'm actually generating the clock. And I'm going to try this super slow setting of 5 megahertz. We'll see if we can deal with that. And that's pretty much all this is. The bottom, that's a little off the screen, but that's just like basically Chip Whisperer boilerplate. We're creating an instance of the GUI and running it. All right, so let's turn that off and do some soldering. I'm going to turn this recorder off and switch to the microscope recorder. All right, how's that? Microscope should be recording. Let's turn on the screen. Right. So, let's see how much we can move this without disturbing it. Man, the fan in this scope is usually the loudest thing in my shop when it's on, and I'm not listening to music. Yeah, that's I don't know how audible it is on the stream, but here it's much quieter with the scope turned off. All right. Okay, I'm going to unplug like all of these things, I think. And I knew what I was getting into when I attached this board on top like this. I just wanted to get the best possible results for the first couple of glitching tests I did, because I wanted to evaluate this in the best light that I could, so I wanted the wires to be really short. So it's a little tight in here. But I'm going to see if I can just tilt this out of the way. Yeah. I'm a little suspicious of damaging one of those solder joints, but I'm just going to hit it with some heat and reflow it just in case. But I think that's mostly fine. A flying glitch board. Let's see how closer we can get with the... I think this needs many fewer wires. Fewer wires, more maneuverability. Ooh, what do you think about the interlacing? I don't know, I definitely de-interlace the stuff that I capture for recordings, but I was experimenting with turning off the de-interlacing filter on the streaming machine to save CPU, because I think that's one of the things that has made it so so tenuous as far as CPU performance goes. So I can see this fine, I just need to angle the microscope. Super high-tech microscope stand is like a lighting clamp and a C-clamp and a sandbag, and that's all. And some bits and pieces from the microscope stand that it came with, that this microscope originally had. Okay, let's get the DSLR view of this briefly. I'm like, I know where I put the remote, and then I'm like, no. Okay, So the critical locations where this is attached is mostly just over here, where I wanted to get it close. Let's get that actually focused. So the critical location is just over here, where everything is kind of clustered around the processor's vCore test point. So that's pretty close to where the action is. It's close to the CPU. It's close to that decoupling capacitor that I want to drain. And I've got a good solid connection to the ground right on that decoupling capacitor. There's another pretty solid ground for these SMA connectors. There's a test point over here that was connected to the ground plane, and I just extended that over on top with some copper foil, and then epoxied these down on top. And similarly, this is just a little mod so that I can inject a clock where the 25 megahertz crystal normally would go. It's been tempting to just pull off the Ethernet jack too and give myself 0.1 inch headers, but I don't think I'll bother this time since this is pretty easy to just like solder some stuff across at this point. And then I've already got a little lead I can just use to run from here to a breadboard. And then over here, these wires are just for powering the buffers, and that's another ground, because more grounds is handy. That ground is closer to where the power comes in, and it's also a little easier to grab with the scope. Alright, just going to improve these slightly since I just put them under all this mechanical stress. Let's add some flux. I seem to, in a lot of these streams, get somebody I notice in the chat complaining about the flux, and I don't know why, because like, it seems to be one of those things like, you get people complaining, like, and the same people who complain about the flux and tell you, oh, the flux you're using is terrible, then they're also recommending that you use the exact same flux they're complaining about. And so I don't know, I think some people just want something to complain about. Yeah. Let's relieve that of some of this stress and bend it back into place. Oh, I think I damaged that capacitor. See that? All right, let's actually maybe replace that. Let's just take off this whole mess. Get that out of there. All right. And maybe now that I have this board, I'll just move the capacitors onto the board. I mean, the other question that I know we could ask is, like, why is it interlaced in the first place? Why would they even bother? And I mean, maybe it's the same reason that they've always done interlacing, to save bandwidth. You know, it makes the parts cheaper, but it's certainly annoying that something produced probably in like 2015 is still using interlaced video. Is that my hand? I guess it is. Let's try to get a better view with that camera. All right, that's an improvement. Kind of blobby, but I think I kind of want that too. That's just another ground. Oh, let me just touch up this other one too, just in case. Yeah. All right. That should do. And that, I guess I should just think of this as an opportunity to move the capacitor closer to the MOSFET, which could only help. I mean, it won't help with the stability of the oscillator, but it'll help with making fast glitches fast. So, I guess I just want to put them, I guess I can just put them across here. Like, if they're small enough, they can just go across this gap. There's also plenty of room over here, but this is a little closer to where the leads are attached. Probably doesn't matter, but let's see what is reasonable to make happen. Let's just give it a couple of 1 microfarad. I think that's what I had on there before. Tweezers are dirty and the board is slanted. It's fine. I should tack it down on one side though, or otherwise it'll just slide off. Having a mechanical joint and a capacitor kind of cohabitate like that was not a recipe for awesomeness. But sticking it up here should be fine. These little LED lamps really help as a supplement to the, both the little ring lamp in the microscope and the overhead lamps. Like, the overhead lamps are mostly for the DSLR's benefit. They're illuminating the area the DSLR is likely to be looking at, and they're good for video, but they're not going to be intense enough for this close-up work. And the microscope has a ring light built in, but it's not the best thing. Not because it's necessarily that bad as far as illumination, it just, you need actually more non-uniformity to see some of the stuff, so having like 2 point sources in addition to the ring light and the room light seems like it's actually pretty good. Okay, so we fixed up the mess there. Down there, that's just the micro with some of the other modifications. Clock input with a little series resistor. And so that's what I did over here. I had hot glued the Ethernet transformer to this board as a mechanical anchor. And I didn't think it was actually glued that strongly, but I guess it was. And this just broke the legs off the transformer, which is fine. I'm probably just going to leave the transformer attached right there because it would be annoying to get off. And we might just be able to run, like, kind of scrape these legs off and then run jumper wires. There are 4 places we need to run wires. In fact, one of the visual aids for this session is probably going to be a schematic for this board. In fact, we can do better than a schematic. We have the Eagle design files for this board since TI makes them available. So we can take a look at exactly what this means, but the typical way these Ethernet transformers are is they have one coil between this pin and this third pin, and another coil kind of on the other side, similarly between the end pin and the kind of third pin. And then that is magnetically coupled to another coil on the other side with a similar layout. And then I think the middle pins are center tapped on one side and no connect on the other side. And then there's also a common mode choke, so effectively another transformer, but rotated 90 degrees. So the signals go through the coils, and then the high frequency interference gets magnetically canceled out. But we're not going to have any of that. We're going to just DC couple this to the cable. And if you plug this in then to another Ethernet card, which still has a transformer in it, then it'll still be isolated. It'll have somewhat different frequency response from having one transformer instead of 2, but it should act mostly the same. But then where it gets a little bit sketchier is going from one transformer to 0, and that's where I'm going to try either capacitively coupling them or just using a resistor, and I'll see how well that performs. We need a little bit more clearance to actually see inside here. That should do it. Need some remnants of the hot melt. Yeah. I might regret this later, but I'm going to add a little dab of glue over here just to take some of the stress off the solder joints. Since it'll be easy to get off later, I think, but it'll prevent this from damaging itself while I'm handling it. So, I do have a great hot glue gun, which I like and I use sometimes, but for something like this, I'll actually often just hit it with, take a little bit of glue and put it where I want it and then hit it with a heat gun. These jumper settings are not something I expect to need to change. I mean, I don't want to rule it out if I don't have to, but they're for things like configuring the CAN bus on this demo board and configuring where the power supply comes from, which I don't really need to mess with. These are always getting tangled. All right. It might be enough heat. A little more, maybe. All right, that should settle into a decent location. Much faster to apply the glue, although it does generally take a lot longer to dry because this adds a lot more heat than the hot glue gun does. I think that's actually contacting more than the... You know, I might actually want to heat that a little more. I don't want to glue it to the jumpers, I want to glue it to the board, and I think that's mostly attaching to the jumpers right now. Okay, that'll be fine. That glue is like fused to the jumpers and probably contacting the board at least, which is what I was going for. But it'll be easy to just cut that off if I need to later. No, those guys are still fine. Yeah, now I've got access to this mess. So this should be easy to tidy. Oh, I could see the smoke and I could smell the hot glue burning, but I couldn't actually see it. It's some like way under there. Right. So we can start to see on this side, those two pins that are like center taps are wired to resistors, R32 and R43. So this pin and this pin are one twisted pair, and they go up through here. And it looks like this might be like a protection chip, like a transient absorption diode kind of thing. But these go through whatever this protection chip is, and then they eventually go to the Ethernet jack. And then that goes to this resistor, that goes to a resistor, the middle two are no connects. And then over here, yeah, these middle ones are connected too. So let's take a look at the schematic to see what that actually is. And then down here you can start to see where it goes to the microcontroller. There's also a little bit of a repair job where I had inserted some series resistors in the past and then replaced them with copper tape after I had done that experiment. So let's do a schematic break here. Yeah, this is from TI's website. You can just download this because it's one of their evaluation boards. So you've got all the kind of printouts for their design. Most importantly, though, they just give you the EagleCAD files. Oh, Eagle, how do you even open files? Let's just get the schematic. Okay, so the schematic comes in a bunch of pages. This is the Ethernet page. All right. Okay. So there are center taps on both sides. I think this is related to just like electromagnetic interference and noise suppression. So on this side, on the kind of non-isolated side, the center tap is connected to ground through a capacitor. So that looks like the kind of thing that would help help kind of ensure this is electrically balanced, I guess. Like maybe it would remove some of the, oh no, that's the 3.3 volt rail. Oh, okay, so that's how it transmits. So it's transmitting by, so like the middle of the transformer is referenced to 3.3. These are just decoupling capacitors to handle these brief current pulses that are getting generated. So to transmit a pulse in one polarity, we're going to be pulling this down to 0. To transmit a pulse in the other polarity, we'll pull this to 0. And then those pulses will cause, so that'll cause a magnetic field to rise and then fall in the left coil, which will cause the same sort of current pattern in the right coil. So here are those resistors we were seeing. Those are 75 ohms. And that is capacitively coupled to the case ground. That's interesting. So this is that, I don't know why they have it labeled U14 here, but that's the, I mean, I assume it's just a connector, but maybe there's something else inside it. Like, so I don't know what these termination resistor pins are on the connector. That's interesting. And then this is the little 8-pin chip that we're seeing. And so these are like transient suppression diodes. And it looks like they've just got a couple of these in parallel for each of transmit and receive. So yeah, I'm not sure why there's a termination resistor for the actual jack here. Oh, I see what they're doing here. This is just the Ethernet jack, but these are unused pairs. So it's 8 conductors, 4 twisted pairs, 1 twisted pair for transmit, 1 twisted pair for receive. They're kind of wired straddling the middle like this, because that's the way the standard is. But then this pair and this pair are both being bridged together and then shunted to ground with these 75 ohm resistors. I'm guessing that's either something for electromagnetic interference reasons or for helping gigabit cards determine that this is not a gigabit card and that it shouldn't try to talk in gigabit speeds. So I can imagine a couple different reasons. So we can ignore most of this stuff, but we might need to care about how the center tap on the microcontroller side is being used here. So, yeah. There are a couple of different kinds of pulses that I would expect to see. So when we're transmitting an actual 10 base T packet, it's going to be, I think the positive and negative will be alternating, but there's also a provision for sending these unipolar pulses, which I think are just used for that link integrity test. So that's possibly what's going on here. think my current strategy is just going to be to wire this, from say pin 1 to pin 16, from pin 3 to pin 14, and just ignore the center taps. But that may not work because of the way these are trying to pull against 3.3 volts, so this might be something we have to revisit soon. Anyway, while we're in schematic land, let's also take a look at the other end of this on the ENC28J60 side and see what it's doing as far as its kind of transformer / driver layout is. And in fact, we might get more information here just by looking at the datasheet for the system on a chip and looking at its Ethernet PHY. The 28J60 also might be simpler because it only does 10 base T. So the first thing to look at, because it's simple, is this. This is the manual just for the board, not for the chip itself. This is what it looks like before being modified. So I've already, can I zoom in? This is the 25 megahertz crystal, which you might even be able to read. So I just desoldered that and glued on my own connector with a series resistor. This is the mag jack, so it has a little tiny transformer built into the back of the jack. And then the actual ENC28J60 chip is on the underside of this board. Oh, they hopefully include a diagram of the interface of the chip itself. Built-in voltage regulator. Here's the physical interface. And so just like the other Ethernet chip, this doesn't have, this doesn't know about the transformer or the center tap or any of this. This just sees two twisted pairs, but we do need to be careful about how it's actually driving those twisted pairs. Can we rotate this? Yeah. Okay. So they're helpful enough to show us the internal schematic for the RJ45 over here. So this looks a lot like what we were seeing on the other side. So this is probably something that's very standard, and it's just a standard technique that I'm not aware of, where you take the center tap on the isolated side of the transformer and then kind of loosely connect it to the chassis ground. So yeah, I mean, it's not even quite the chassis ground. So they've got this kind of virtual ground that they're creating and kind of tying down the center of these two transformers to kind of give them like a virtual ground reference. So these, the other two, like the two end terminals of this transformer coil will appear to have a balanced differential signal on it, and this will end up near ground, which seems reasonable. The choice for these values are probably some compromise related to interference and safety, though, rather than performance. But yeah, it's pretty much the same thing we saw here. And then the center taps here, on the receive side, it's not connected at all. And on the transmit side, that's interesting. Oh, I see. This schematic was just confusing. So on the transmit side, the center tap is referenced to 3.3 volts. So just like before, it's going to generate positive and negative pulses by kind of pulling one side of the transformer down to ground. But then, effectively, so this ends up kind of being in parallel with each side of each side of this transformer coil is basically wired in parallel with one of these 49.9 ohm resistors. So I'm not sure what they're doing there. That might be something for calibrating the current that is actually put into these transmit coils. So I think this is something the data sheet for the ENC28J60 recommends. So this is probably something to do with shaping the pulses on the transmitter. But even though it doesn't really look like it, these TP out and TP in, the way they're labeled here, they're connected to the chip over here. So I think what we want to do is just desolder this whole mess. Just take the connector off. which might even just mean like levering it off, since I don't know if we'll be able to get it hot enough safely. So probably mechanically desoldering this thing, and then just running some breadboard wires to this. And so what we might need to do, so the receiver is expecting, I was going to say the receiver is expecting something pretty high impedance, but actually, so in this case, the receiver is kind of got this load here. These 49 ohm resistors are acting like a shunt across the signal that's being received. So it's actually kind of like this little thing I made. So I was trying to just measure the signals coming out of an Ethernet transmitter, and so you can't measure a current being induced in a coil without giving the current a path to flow through. So you could short out the coil, but to have a more realistic load, I'm using, I think, like 75 ohm resistors here. So I think they're using 50 ohms because that is supposed to be the characteristic impedance of the line. This is just what I had handy, but I think 50 ohms would be better. Or something like this. This little, I just took a RJ45 and put some surface mount resistors in it so that I could use it as a load. So terminated each of the pairs. So if you imagine what would happen on this circuit if I just were to wire, imagine the other side of this looks the same, which it does. They both seem to be using, well, I should look to see what the termination resistors are on the other side, since that could end up being different. But the driving strategy is the same, having the middle of the transformer connected to 3.3 and then pulling them down. Okay, these are the termination resistors. So these are terminated to 3.3, whereas over here they're terminated to, well, to a capacitor that's attached to ground. So that might need some modification, because at yeah, I mean, I would expect that I would need to maybe change this termination so these are connected to ground, so that the transmitter on the other side ends up yeah, I don't know. I'm going to stop speculating so much, because a lot of this I think depends on whether it's using a push-pull driver or not. Because if it is using a push-pull driver, then this matters a lot less, especially at super underclocked speeds. So yeah, I think for the moment I'm just going to try connecting it straight across, but there's a possibility we might need to modify some of this termination, and I'm thinking that maybe the modification involves just having like 50 ohms to ground, I want to say. But maybe 50 ohms to 3.3, and this is why I'm wondering like what the driver in the chip looks like whether it actually pulls up to 3.3 and pulls down to ground, or whether it's just expecting to pull, like if it's an open drain output and it's just expecting to induce current in one polarity using the TX positive and in the other polarity using the TX negative. So we might be able to find that by combing datasheets and specifications, but that's also really easy to test with the scope once we hook this up. And I don't think that any of this looks likely to cause problems other than just not working if we hook it up and something isn't right. One thing that I worry about is DC current flowing through, so when we connect them together, I might initially connect them through like a 50 ohm resistor just to be safe, but I think first step is just to put these wires in and then see what this looks like on the O-scope. Let's see. Attempting to catch up on chat, but I think I might be a little too far behind until I have more of a moment. Such a cat. Do we have microscope? Yes. Let's see what kind of wire fits this problem best. Maybe, is 26 too big? These are really big pins. I mean, that should be fine. That doesn't seem too big. Let's see how long this wants to be. Let's get in there and mark the length, and then cut a few wires of that same length. About that long. So I just need 4 of these. Peaceful cat. I wouldn't have carried him down here and just like sat him on the chair unless I had a pretty good idea that he would enjoy that. Because he had a pretty comfortable place upstairs too. But he seems to like hanging out. All right, 4 little wires. Let's have fewer things in the way. Oh, it might be warm enough I don't need these sleeves. Oops. Sorry, Tuco Cam. Just expecting to tack it down, but maybe I do need to put some more solder on this first. Yeah, there's not even enough solder to tack that down. Let's just do that. joint. Oh, I think the wire got a little bent and I didn't quite notice. That'll hold for just a minute. Part of the reason this doesn't adhere is that the wire is not tinned really, so it's going to take a little bit of heat and flux to prepare the wire to receive any solder. And I would rather do that when the wire isn't quite so awkward to hold. And I could tin the end before putting it in. It might have been easier. Where is that shadow? Ah. A little too delicate there. Good enough. So I think the first thing to try once this is all soldered is to just look at the waveforms and so at first we won't see any data, we'll just be seeing the pulses where this is trying to detect a link. One potential issue is it would be really nice to just test this in isolation without the other end and just, I mean for both sides. And it's a little easier to send traffic from the ENC28J60 side since that's connected to something we can control more easily. But it'd be nice to be able to test just one side on its own to see if, like if electrically I'm getting something that seems like the other side would be able to receive it. And part of the problem in getting to that point is, that's also not very good, but I felt the other side starting to come loose. So part of the challenge in getting to the point where I can just like send a packet into the void and watch it on the oscilloscope is having a link detected. So this normally won't even try to send something if it doesn't think anyone's listening. So if it hasn't received one of those link detection pulses from the other side recently. So one way we might be able to get away with that is just to have a function generator generate link integrity pulses, because then we could actually try a range of different pulse settings and see what qualifies as a valid link integrity pulse given the crazy underclocking we're doing. And then we won't have to worry so much about compatibility between two devices. We could just get both of these devices working in the extremely underclocked state and then get them talking to each other. Underclocking is much more straightforward. We don't have protocols that are quite so ubiquitously just baked into hardware as Ethernet. But luckily with Ethernet, with like 10 base T, especially super slowed down 10 base T, it would be easier, like relatively easier to get a much lower level way of speaking this if we needed to. So like I'm imagining, I mean at these speeds you could probably even bit bang it with a fast enough microcontroller. Just use GPIO pins to, in software, speak the Ethernet protocol. But definitely an FPGA could handle this. And it's just that the actual physical interface layer, which is like this transformer that we're messing with right now, is what starts breaking down when you change the speed this much. Come on, wire. This wire is not getting hot enough, and it probably needs more flux. Flux pin. That one was not really strong enough to withstand the flux pin. Wire. I feel like the top of it is not really doing its thing, but maybe it's fine, and now it just has too much solder. My phone is buzzing with something from Twitter. I wonder if that's urgent news for the stream. That's better. Yeah. That is way too much. Yeah, I think the plating on these little pieces of wire was just a little weird, and I didn't have nearly enough flux involved. No, it's better. I still often really underestimate how much flux I need. I think part of me is just like, flux, that'll just be gross. I don't want to have to clean off flux, but oh my god, it's so much worth it. It's so worth it to have good flux. Oh, this wire is not straight. Just have some more flux on this side and maybe a little bit more solder. And yep. That's fine. Okay. All right. let's see where that gets us. Before taking the other transformer out, let's just see if we can test this possibly with the less severe underclock. And I also want to just see, like, electrically, are these even driving, or does it need something to drive against, like a pull-up or pull-down resistor? All right. Let's put this back too. All right. Yeah, I was thinking about doing a test, but actually, I think I want to just take the other transformer out too, because switching between soldering and having everything plugged in and running is a bit annoying. So, slight change of plans. More soldering, then testing. So for that, let's take a closer look at this camera. Oh, somebody keeps mentioning a bunch of documents that I need. Ugh. Apparently, I really need to check out this thing called SNLA 088A.pdf, which actually sounds very familiar. That's not just the schematic for this board, is it? Because I've read that. SNLA. A Transformerless Phi. Yeah, no, that's, I mean, interesting. Okay, so this actually isn't a special Phi. This is, oh, that's great. Okay, thank you. This is definitely not something that I'd seen, and it's very applicable. Let's put this on the screen. This comes from US Water Rockets in the chat. This is pretty much exactly what we want. So, and we're talking about biasing and DC isolation. So what have we got? What have we taken off? So here's the Phi, which is, I mean, this document comes from TI, so this fighter thing is the brand name for their like standalone Ethernet interface chips, but it seems likely that this is similar to what they're using in their silicon. So this shows everything being biased up to 3.3 volts, which is consistent with the way the coils were wired. So this would be able to transmit by pulling them down to ground. And then here, we're just blocking DC with these capacitors, and then there's nothing special for like balancing on this side. And this doesn't have to treat the transmit and the receive separately, so that's nice. And I mean, we're going to need higher value capacitors here, or probably going to need much higher value capacitors, but all right, that's interesting. I think this is pretty much what we were going to end up with the possible exception of this resistor network here. But yeah, I think this works pretty well with the plan of just continuing to pull off the other transformer and then having a breadboard where we can play with these capacitor and resistor values if we need to. Does this have any info on the driver? I mean, I'm sure the info on the driver is like in the PHY datasheet, which I could look at, but it's not necessarily such a worthwhile rabbit hole right now because it doesn't really change the next couple of steps I'm taking, and it's really easy to determine experimentally in just a second. I think these pull-up resistors are, like, I think these are the ones that are near that copper foil thing that I briefly pointed out on the microscope. That little modification I made. Anyway, it's a little hard to get on the microscope right now. Anyway, that was a nice datasheet diversion, but I think the next step is still to do some connector removal on this thing. Alright, so this is what we've got. Oh, this is about to stop. Alright, so this is just connected to the SPI port on the Raspberry Pi, which we can take this out if we want to. And I mean, you can find some guides online that have the same wiring in them. And then this is the external clock. And then this is the actual module. So there's the mag jack. And my main goal here is not to remove the mag jack cleanly, but to avoid damaging the rest of the circuit board. So one option would be to desolder these pins. They're pretty close to the chip, and I definitely don't want to damage the board, and I don't want to overheat that chip. So one option would be to cut these front pins by going in with diagonal cutters, like right under this edge of the board, and then just kind of lever the rest of them out, and that'll damage the socket, but probably not the board. The other option is just to kind of disassemble the back of the socket by, like, it looks like this comes off, and then maybe you can get to the transformer inside and just kind of remove it. I'm going to try the first strategy because from what I remember about how these are made, taking off this back part still doesn't get you that much as far as access to the connectors because there's usually a blob of glue in there. So in the front here, these are actually just LEDs, which are convenient, but that's fine, they can go. And then this doesn't have those, oh yeah, it does. These solder joints are the shield, and then it's also got these plastic snaps. So let's see what we can get through. Seems so good so far. Let's not be no conductive debris on the Raspberry Pi, please. Yeah, that seems like it's working, but more likely to damage the board than just opening the sheet metal. So, where's that open easily? And we can start to take off the shield pretty easily. This is also now negating like pretty much all the benefit of having a breakout board for this chip. So like if I had any of these chips handy, I would probably just start with a bare chip at this point. Oh, this is different from other ones I've seen. This one looks like it actually has the same kind of little transformer you would see in a through-hole device, but attached to a tiny circuit board in there. And some of the other mag jacks I've seen, the transformers were just like epoxied into the case. Alright, and that's attached. I think I can just metal fatigue that away if I need to. The little wire, you can see that? I guess that's ground for the circuit in the mag jack. It's funny. The connector end of the connector. Seem to be unwrapping it alright, but I still might end up needing to use some of the same approaches to get this off the board if I actually want to get it off. I also might just be able to get to the signals I want, but it's kind of annoying having the plastic in the way where it is. Pretty. Close quarters here. I don't want to damage any of these signals I care about. Oh, I think I can avoid taking off the LEDs if I want. I think I can just cut the LEDs out of the socket, kind of. There's a little piece of plastic I just have to kind of cut off. It's actually just glued on. It's like a little thing that's glued over the LEDs. That's strange. These are just little like, kind of 3mm, but with a kind of an oblong lens. Just regular through-hole LEDs that were glued into just the right spot in their plastic mold, I guess. Connector carcass. There's the little board. Cute little thing. Tiny little transformer right behind the connector. All that's left now is, so that's interesting. This is, once you remove all the plastic molding and the kind of connector itself, the little spring pins, this is a really thin circuit board, and a little actual PCB mount right angle connector that comes out at the right spots to make the kind of staggered footprint they wanted. So that's kind of cute. Let's see if I can destroy it. Not bad. Focus. Try to do this without scratching the circuit board too much. Oh, Tuco's dreaming. You see that? The twitching? Okay, I think I need to get slightly more aggressive with this. I was trying to be gentle. Oh, we've hit bedrock. Tuco, how was your dream? Saw that coming. A little bit of blood. Yeah. Don't try this at home, kids. I was trying not to scratch this board, but I did scratch it a little bit, just not in a way that should affect anything. It's not bad. I mean, I was more worried about heat damaging it, so I'm glad I didn't have to get this thing super warm. And somehow preserve the LEDs. And the backside's fine. So I think at this point, I'm just going to solder jumper wires to the ones that matter. Let's verify which ones those are. Let's actually switch to the microscope, because this is kind of at the limit of what the DSLR can handle. Oh, here's the thing we got out. That'll definitely be more interesting under the microscope. Okay, microscope. Yeah, small flesh wound. That'll be all right. Microscope. Let's hit this with something. That's pretty. I've often been curious with these particular transformers how much of this process is done by hand and how much of it is done by machine. These coil winding machines are pretty neat, but it's also still a pretty neat area where, you know, there's like overlap in the skills between, you know, like making things with beads and making things with high-tech electronics. And then pretty thin circuit board. Let's check out the other side. Oh, it's even got writing. Viva 75 ohm. Yep. CCT 1 nanofarad. I've never seen a silkscreen printed with like a dot matrix quite like that. That is a little weird. And that's what we've got. So I want to clean that gouge and make sure there's nothing conductive in there, but it should be fine. Nothing important damaged on that side. Right, this is probably going to have, this has all that extra termination. Pull up the schematic of this module, just to have that handy too. All right, so we should see the stuff that was on the outside. And mostly we're looking for, I just want to make sure I know which ones receive and transmit so I can put the jumper wires there. And it would also be nice to have the footage where we correlate these two things. So that looks like our 10 nanofarad to ground. Oh yeah, these have designators. So R5 and R6, that's our transmit. Those two. So if this is following normal RJ45 pinouts, oh, gotcha. The mag jack does not have a normal RJ45 pinout because of the center taps. I only see 8 pins here. Oh, gotcha. So it doesn't have. That's also weird because like they want this to fit in like a similar amount of space, I guess, to a traditional jack which has 8 pins, but they need the center taps, so they kind of swap the center taps in instead of the other pairs that otherwise would have been unused. So that's a little weird. So not quite a standard RJ45 pinout. So in that case, our transmit, our T plus is going to be on R5. So this is T plus, T minus. Then TP out. Oh, why is T pin not transmit? Oh, twisted pair in. Ha ha ha. Okay, so those are our inputs. Then our outputs are over here on R3 and R4. Yeah, so just on the other side. R4. So this is the common. Yeah. So that's the center tap. It goes to R3, R4, C9. Is that the 100 nanofarad over there? Yes. And then L1. Great. So I just want the 2 pins on either side. That's easy to remember. And positive is on, this one's positive. And, okay, so on both of these, positive is on the bottom too. Okay. Maybe I can label that somehow. I want this to be reflected in the wire that I choose, I think, but I think for now I'll just put a little plus on the bottom side. All right. Let's also maybe label which side is TX. So in is R5 side. And the outside. Right. There we are. And as bonus, my hands are covered in blue Sharpie. That's awesome. So, what is that? Okay, so that is a gouge into the board, and there's a little bit of copper that might want to come off. Let's just help that out a little. Okay, that's fine. I just don't want my out there shorting to the ground plane. And so most of the stuff that looks kind of ambiguous here is like a gouge into the fiberglass, but there is a bit of a flapping around layer of copper up here that I wanted to take out. There's a little bit of that down here too, but not so severe. Alright, some jumper wires. Oh, let's use some actual twisted pair for this, because that's easier than twisting jumpers together, I think. I'll just grab a scrap of Cat 5 from the bin. Yeah, the Ethernet transformers are pretty important for most situations. Like, it's mostly a safety thing. It's also partly an electrical signal integrity thing, but both of those kind of stem from this problem where you have these two pieces of equipment on the end of a long wire, and they don't necessarily have the same idea of what ground means. So like if you had a really long voltmeter with superconducting cables and measured the voltage between those two grounds, you might actually have a pretty big number. And so that's part of what this does. It isolates those two devices. But in this case, I don't really need or want that because the two devices are really close together and they're even running off the same clock. They definitely have the same ground. Let's use maybe a standard. I kind of want to use the standard colors, but I'm likely to get it exactly halfway wrong. I think I want to put green on the left, but we'll see. It also doesn't really matter because of the like automatic switcher thing. Like if I get the polarity wrong, it'll just use the other side. Not this device, but the other device. So I'm just going to strip a little bit off this. Even like with long distances or like challenging electrical power situations, the Ethernet isolation transformers are especially important. But you know, for like safety reasons, but even much smaller differences in grounds can cause like more signal integrity problems. With Ethernet, it's more like, it has to be within a certain range, otherwise the receiver just won't work correctly. The ground loop issues you might have heard about in audio are because that's a much more sensitive signal that's also referenced often to ground rather than to another kind of differential signal. That's right, I was going to tin these first. This streaming setup has so many audio transformers in it because these little USB HDMI grabbers just generate so much ground loop interference without separating them from the analog audio. Right. That was not good. And it wasn't terrible, but it's not going to give me a good joint. If I was doing more than just these two wires, I'd probably bring some kind of like alligator thing over to help hold them. It's also easier when I'm not trying to get it under the microscope. Alright, I think it's tempting to use these little posts, but it's also tempting to pull them out because I've already lost one. Hello, train. It's obvious on the microscope when someone moves something like in the hallway or next door. For a warehouse building, the floor is not quite as stable as you might think. Alright, let's just have a little solder ball on the pins we want to solder this to and then join them. It's much easier than actually trying to force the wire through this hole. great place for a shadow. Alright. Yeah, these will do for a little test jig like that. Alright, kind of ugly, but totally sufficient for this. So I'm just going to put a matching, when I say matching, so I made this other thing earlier that is just a tiny Ethernet cable that I can plug into a breadboard, and I kind of want to use this similarly, so I think I'll just terminate this with a small, like little 4-position header like that. Then I can experiment with using this little breadboard to couple the two together. Oh, I wasn't paying attention and I just snapped off 2 of these when I wanted 4. Let's get 4. Let's use that to hold these. Can stick this back on the Raspberry. Yay. Raspberry Pi with the power of strange base T Ethernet. So then these, we'll prepare them a little. I feel really sorry for the autofocus when I do stuff like this, because this must be super hard. Putting the breadboard in the vise is a little unnecessary, but it helps me get it to the right height for the microscope. Try to keep these semi-consistent. A little thicker than what I want, but I don't like squeezing with the tweezers. It's easy to overheat these headers and hard to get my my hand in the right position. That's better. Yeah, these pin headers are not super heat resistant. I haven't seen any that are, but it seems like something where if you wanted to make like boutique project or products for prototypers, you could sell them like really nice pin headers. But I tend to be appalled by how expensive pin headers are from like DigiKey, so I'm often like ordering them off eBay. That's right. Easier to form these first. That'll be fine. Alright. Ethernet, brought up pin headers. I think now we're done with the kind of soldering related stuff for the moment, and we can start plugging things back in and making the clocks go again. Set lights. Alright, so many objects. Chip Whisperer and the FPGA with the clock PLL on it, and the Raspberry Pi and the Raspberry Pi's Ethernet. Alright, so first I'm just going to take out all these resistors and just look at what happens without anything connected on the scope, which will tell me a few things about this. And then I might just try capacitively coupling these two kind of straightforwardly and see how far that gets me. This insulation is so stiff. I think I might want less of it. Looking at the monitor while the cutters are directed into your thumb. Great idea. Alright. Okay. Little stubby Ethernet thing. Alright. I think this is safe to power on at the moment. We're good on the conductive debris front. This needs to be plugged in. There's some kind of conductive debris killed my father joke in there or something. Alright, so power. Chip Whisperer gets some power so it can generate us some clocks and capture us some datas. And then the clock PLL FPGA in here gets some power. Then this cable is supposed to go into the board under test for powering it. Oops. Still very slidey. That goes over here. There we go. And the last one is the Raspberry Pi, which I'm going to wait to plug in until I get the clock set up. The Ethernet driver will not be happy if it doesn't have a clock. Thanks, movie recording. Oh, am I filling up this card? Maybe not. Okay. Clock is on the computer. Alright. So, Chip Whisperer VM. Cool, it's still already connected. Just gotta restart the software. So I'm just running that same script. Alright, so that should have set up the clock generator. Can run a trace, but we won't see much. I mean, the HTTP is timing out, and then the trigger is timing out, and then it's giving us a trace, which looks fine, but is not really interesting. And just want to verify the clock before I power this on. I'm often grateful for being able to scooch a 0.1 header just a little bit off of its connector, just enough to slip in an oscilloscope probe. It's always annoying when I have to come up with some kind of other interposer solution. That is the right scope probe. Oh, right. Next up, I've got the clock set up, but I have not loaded the clock synthesizer into the FPGA. So that we already went through in a previous stream. I've got this binary compiled that I just load into the FPGA, and now I've got a clock. Is it any good? Looks fine. So that's our really weird low frequency. It's the 1.042666 megahertz. So that seems to be what the scope is telling us when it's picking up the right harmonic. Yeah. 1.042. Let's get a closer view. So yeah, and I haven't changed any of the parameters for the PLL on the clock generator, so it still thinks it's generating a 6.25 megahertz clock, and I'm just underclocking that also, which seems fine so far. I can always change that if this PLL has stability problems. All right, now I'm going to plug in the Raspberry. And let's see if the Raspberry can start talking to us. We should at least be able to see it generating, we should be able to see both sides actually generating these link integrity test pulses. So I'm going to leave the clock on the scope actually for a moment and just grab this on trace 2. And I'm going to cheat a little bit and get a ground from way over here, which isn't great, but the signals are not going to be especially fast right now. So that's kind of nice. It's nice that we're seeing these hanging out near 3.3 volts. So like we don't have to worry about biasing them additionally. Well, that was on the ENC28J60 side. If we go over to the other side, the TI side, these are all floating to a much lower voltage. It's like 1 point something. So I might need to add additional biasing here. If that's even on, it also might just not be initialized. Well, let's see if we can get link integrity test pulses here. Not seeing anything interesting here, just this interference from the clock. Let's see what the Raspberry Pi is detecting. I mean, I've operated it at this frequency before, so we should still be in known territory. And I would expect the Raspberry Pi to be seeing this adapter just fine. Raspberry Pi is alive, and Ethernet is there. So, got that. We just aren't getting any interesting pulses here, so maybe there's something we're missing. Or maybe... Oh, I might have been looking at receive also. I keep forgetting that, unlike the TI thing, the TI chip transmits link pulses on both the transmit and the receive, because it doesn't know which one is which at first. But this one... Oh, is that it? That looks like it's just an especially large noise pulse. No. I think we might need... we might need some resistors or something. These are all just close to 3.3. I mean, it's already got these pull-up resistors. Like, I would expect to see a signal on here. Oh, maybe I had these two backwards. Maybe I was probing this one thinking that it was going to the Raspberry Pi, but I didn't see the loop in the cable. Okay, yes. This one that has all the ones, or all the pins, the plus and minus on the RX and TX going up to +3 without much going on, is the TI. Which could be fine. We haven't really looked at the state of it, so it might not even be running right now. But I meant to be looking at the ENC28J60. It's just this cable is going to that. And so that, I'm seeing them all idle. What is that, like a volt or something? Yeah. We'd like more pixels on this. Average voltage, 1.15 volts. And do we see any deviations from that? Not here really, but let's try the others. Oh, was that it? Yeah, there's our link integrity test. They're just slow. Let's make that bigger. All right. So they're not very big or very fast, but there's something trying to transmit. So I think we're going to get that. We're only getting that on one of the oh, here we go. So the other transmit pin is going negative. I guess that's what you would expect if it's trying to send a unipolar pulse. Yeah, that's really not the pulsiest pulse, is it? I'm wondering if, I don't know why the edges are so bad looking. I mean, my first intuition is this has something to do with those 50 ohm load resistors, but I mean, I assume this is designed to drive into 50 ohms. They just might, things might be different now that we're running it at such a weird frequency. But that seems plausible then. So if these are the receive, they're just kind of idling and not doing much, and then the other pair is transmit, which is giving us something that looks kind of like a link integrity test. One thing we could try is just doing like a loopback, just connecting transmit to receive, and see if the Raspberry Pi detects a link. I don't know if this will work, but I think it'll be a quick test, and we might as well try it. Yeah, so right now, the Raspberry Pi is telling me ETH1 is our underclocked adapter, and so it's up, which indicates we're telling it to try to work, but it doesn't have the running flag, which it would have if there was actually a link detected. So that's what we're going to try to get, just by putting some wires in this breadboard. Wow, that was easy. I didn't expect that to be so straightforward, but I guess we can receive those link pulses we're transmitting. Let's take a look at this on the scope, because it's kind of interesting. We might also be able to transmit packets too, since we have this fake link going on. We'll just get them back ourselves, and the local Ethernet card will ignore them. Okay. Let's get something to synchronize with. Just going to plug this into one of the two signals. And there's our positive link integrity pulse. We're getting a lot of this clock interference. I think that's mostly because of the way I have this oscilloscope probe connected. I don't think necessarily all that interference is perceived by the device when I don't have the probe connected, but it's because I don't have a really good ground connection for the Ethernet wires. I'm just grabbing that from way over here. And if I put the scope ground on the other Ethernet connection, then that would be bad. That would be shorting that out. Like, to get a clean signal, I could probe both and subtract them, either in the scope or with a differential probe, but then I wouldn't also have the clock signal on screen. And the clock signal, I like it. Just nice to see this synchronized. So let's see if we can transmit packets. I'm going to just do a ping to some IP address that doesn't exist. And so we can see something going on. For a more reliable stream of pings, so the ping actually doesn't directly send a packet. It's first going to try to look up the IP address, and what we're actually going to get is a failure to look up that IP. So to get a more direct way of just like sending a packet out into nowhere, I'm going to do an ARP ping. So yeah, so when I was pinging just this address, I get some packets, but that's really like ARP requests. That isn't the ping itself. So the timing here is a little hard to debug. But there's another handy program, ARP ping. It only has one P. And I can tell that specifically to use ETH1. And then I can just ping something that doesn't exist. And so it's not getting a response, but it is still sending out this ARP request each time. And to make this easier to trigger on the scope, I can set the delay to be much smaller. It'll be really easy to overrun what this slowed down chip is capable of handling. So this signal looks so bad. I'm going to have to find a slightly better way of getting this through. But you can see the packet in a couple of pieces here. There's like a preamble, which is the stuff that doesn't change. That's just indicating that it's the beginning of the packet, and it gives the receiver a chance to lock onto the clock frequency. And then, you know, it might be that the link integrity pulses are being generated using some mechanism that doesn't scale with the underclocking, because this seems like it should be bigger. But anyway, after that preamble, then we have the actual data contents of the packet. So we could try a similar experiment with the TI chip, but you know, I think I might just try capacitively coupling these and see if I can talk. One slight step to do before that is just to make sure the microcontroller is running. So I want to make sure it's speaking to me on serial. I think this is still connected to its serial, and I'm just going to reboot it and see if it says something. Yeah, this is... The reset button is having an effect. When I press that, one of these green GPIOs goes on, or goes off and then comes back on when I let go of reset. But I'm not getting... Oh, that's because the scope probe needs to go back in place. That's right, this needs to connect to the serial port so I can tell if it's working. Great. Let's actually make sure that this is running at the speed we expect it to. So normally this is running at, normally it's 120 megahertz, and this is 115, 200 baud. But we are downclocking this to, what is it, 5 megahertz? Is that what we were hitting? Yeah, 5. So this is actually going to be 4800 baud. It should be the same as over 24. Yeah. Right, these cursors. That looks right. That's like within a pixel. It's about 5 kilohertz. Okay, so our processor is running. Let's see if we can get these two connected again. And for that, I'm going to use something similar with this ART ping, but I'm going to be going for the address of the board that actually exists, and somewhat longer delay. All right. And some capacitors, maybe. Yeah, I don't think the value for this is going to be super critical, since I mostly just want to block DC. I'm not going to really worry too much about the spectral response of this as long as the packets get through. So I want to use something on the high side. So these are 0.22 microfarads, which should be plenty. So I need 4 of these. And I'm just going to wire these straight across. Okay. Now, it's not magically working, but let's diagnose it. Oh, I think I'm seeing a link integrity pulse. Let's get the scope back on the screen. There's so much noise going on, though. Let me see if I can get a better ground. Okay, that is not something an alligator clip can actually hold. Alright, cool. So we have them capacitively coupled with this 0.22 microfarad, which is effectively a wire for the frequencies we're interested in, but we'll keep DC current from mucking up our receiver. And I, at this point, just want to make sure we're getting link integrity pulses on both sides in all the applicable polarities. And so this orange side, I think this was the side where the TI chip is transmitting. We're getting link pulse. Let's verify that to see which side that's coming from. Yeah, it goes away if I unplug the TI chip. Doesn't necessarily come back when I plug in the TI chip, though. Do I have to reset it? I like having tests that are reproducible in both directions. Like, you break it, you unbreak it, you break it a couple times just to see if you really know how. And I don't like it when that doesn't hold. It could have chosen the other polarity, maybe. Is that what happened? I thought I saw a link integrity test pulse. Let me try AC coupling this. Oh, what are you? Oh yeah, maybe we won't be getting link integrity pulse packets if I'm flooding it with ARP pings, because they're only necessary when the line is otherwise idle. So is this something the Raspberry Pi is transmitting then? The Raspberry Pi is transmitting on the orange wire. So that's what this packet is. Does that mean the Raspberry Pi thinks it has a link? You can check that from the terminal. Oh, and they do go away when I cancel the art ping, which is nice. Yeah, it's running. Well, okay. Maybe things are kind of okay. Like maybe I can transmit, and maybe I can get link pulses. So this might be a problem only on one half of the connection. So we're still not getting responses, but so this is coming out of the Raspberry Pi's ENC28J60 adapter. Let's readjust to CoCam. All right. Why am I only getting link pulses now? This is definitely one of those problems where just like correlating things between a terminal window and the O-scope, where you really want to remove externalities as much as possible, but you can't always. And you know, sometimes the operating system decides to transmit something you didn't want. And wow, okay, we've got a much better signal here. That's the preamble. And then there's the data. So this is, oh man, this is really slow. What is our actual bit rate here? Let's find some bits to measure. I mean, it should be 10 base T over 24, or whatever that is, if somebody wants to do the division. But I'm also just going to measure these bits because I have them here. So I think one bit is 2 of these periods. So one of these periods is like 455 kilohertz. 2 of them is like 208 kilohertz. That seems right. 416 kilohertz. That's a good speed for a network. Yeah. So I think we're fine on the transmit side on this. I was a little worried that the ENC28J60 wouldn't be quite up to this much of an underclock, and I would either have to build something custom or use another one of the same chips that I'm trying to operate on. So let's just make sure that's getting across the capacitor. That totally is. Great. In fact, it looks even nicer on this side. And the other polarity is good. Alright, so are we trying to respond at all? This should be where the TI is transmitting from on the green wire. And this is maybe where I start to care about DC bias levels again. Oh, was that a link integrity pulse? I feel like I'm hunting a Yeti or something. Oh, it is. That's a link integrity pulse. Yeah, it's not bad, too. So that is coming from the TI doodad. And it's kind of synced to the other clock. I don't know why the pulse looks the way it does, like the shape. That is really weird. Like sometimes it has this kind of pre-pulse and sometimes it has this kind of post-pulse. I'm not sure what would be causing that. Oh, time for the next card. Oh, need to format this. I'm such a cat. Okay, so I mean, and we're getting this link pulse. Otherwise, it wouldn't say running. So we know that. And if it's not trying to transmit another response, which also seems to be the case, then it might just be that this packet was not intelligible by the microcontroller somehow, or something, something is going wrong on the receive end. So maybe that's where we take another look. So the TI is seeing this across its receive input. I don't know why these pulses are so slanty. Like I would have. So I would expect that the physical, the like electrical line drivers in the Ethernet PHY, like I would expect those to be tuned to have a particular slew rate so that maybe when they're operating at full speed they look like this. Maybe, I mean, I would expect them to be even a little cleaner there. But then slowed down, I would expect that with a slower clock rate but the same electrical characteristics on the chip, I would expect to see actually pretty steep edges. And this is not what I'm seeing. So that's interesting. This is through the capacitor. And again, this is the stuff that's being transmitted by the ENC28J60, so it also might be that we just, yeah, that's before the capacitor, which looks a little better. So maybe it helps to increase these capacitor values slightly still. But even before the capacitor, it looks pretty bad. And I'm wondering if maybe, I'm wondering what this would look like if I messed with those 50 ohm resistors on the ENC28J60 board. And those might be necessary, but those also might be slowing it down. I also want to see what the differential signal looks like, so I'm going to sacrifice my channel 1 since I'm pretty happy with the clock alignment. And let's look at the other half of the differential waveform. If I can duck under the microscope or under the camera. Let's use this probe. All right. That's not terrible. It's the alternating part of the party there. I mean, so like I'm surprised that it looks this slow, but it seems like this would be intelligible. Let's see what it looks like when we add these together. Or subtract them, rather. So that bottom trace that is in the almost invisible dark purple is the just the subtraction between the two. So actually that's a little bit illuminating. That looks better than either one, which kind of indicates that like the two individual halves of it are just driving, it's like I can imagine those driving like two halves of a pulse transformer and kind of adding their half of the waveform, and then what you actually want is the kind of balanced version on the bottom. But that should be what the receiver can see. I mean, I would expect the receiver to basically be an op-amp doing this kind of subtraction, but So there's a question in chat about whether pull-up resistors are required or whether the drivers are push-pull, and that was a big question I had. I think the answer is the drivers are push-pull. The pull-up resistors are still in there right now, but yeah, I think maybe the next thing to try is to remove the pull-ups on the side that's transmitting right now. Another option that comes to mind is to try this test in the other polarity. So right now, all I'm testing is transmitting packets from the Raspberry Pi to the microcontroller. And it'd be nice to do the opposite. I just don't have an easy way of having it generate traffic right now. I'd have to recompile its firmware, and that seems like an unnecessary diversion because I need this side to work anyway. Yeah, where are those resistors? Oh, Tuco, you are beautiful. Aw. Yeah, so this is the transmitter again. So this is the part we're looking at. And certainly is tempting to just try pulling out R3 and R4, because that seems like it's providing like a lot to fight against, especially for low frequencies. It might just be that the driver in here is optimized for providing a higher current pulse at those high frequencies, but when I turn the frequency down, it's kind of struggling against R3 and R4 perhaps. So yeah, those are on the bottom side, so we're going to have to power this off, or at least the Raspberry Pi, and flip that over. Right, Raspberry Pi is off. I think I can leave most of the rest of this in place and just pull it out. Tuco is a big fan of chairs. I think maybe even more so than I am. I sit in chairs a lot when I work, but I also like sitting on the floor. And Tuco does that sometimes, but I think he sits in chairs more often. Yeah. I will put this under the microscope just for getting the footage, but it would be easy to solder without the microscope. hanging out somewhere else interesting. He likes those stairs. I gotta figure out where to put them up so that he gets access to something new, hopefully. Alright, recorders are going. It's tempting to remove something like this with hot air. But I think I might just do it with the iron. Let's grab that slightly better. It is not grabbed very well right now. Yeah, that's better. Oh, my soldering iron fell asleep. Warm up, little soldering iron. Here you go. Cat's got some good yawning action going on. Alright, iron is hot again. At least this one heats up fast. This resistor might be a little too big to get off using this method, but... Oh, there it goes. Just wanted to see if I could avoid heating up the whole area again. Just because I would be a little stuck if I broke this particular ENC28J60, because I don't think I have another one handy. I guess I should throw another one of these or two into my next DigiKey order. I looked away for a second and the resistor disappeared. Did it stick to my solder? Another for the conductive debris bucket. Alright, well, I don't see the conductive debris, so let's clean this up and flip it over. And see how that affected our signal. I wasn't even paying attention to these LEDs earlier to see if they still worked. Okay. Oh, I just put that camera right in the worst possible position for me. That'll be fine for now. I think the next step is to plug this back in and let the Raspberry Pi boot. Oh, come back, little guy. How's our clock doing? Tuco, why are you messing up the chair like that? Is it because you're a cat? Oh yeah, Tuco's back. I guess I can move cat cam again. Aww. Tuco, do you think that piece of paper I left there is important? It's like the shadow of the Mars lander or something. Maybe he'll hang out there on top of my timing diagram. Alright, I wanted to check this clock before booting the Raspberry Pi, just to make sure that worked. It's not like it would damage anything, it just makes for very hard to diagnose problems if when the Raspberry Pi starts up this doesn't have a good clock. That's better. .042 megahertz. Alright, so Raspberry time. Ooh, yeah, solder is the worst conductive debris. Let's not let that short stuff out. Alright, and we're going to look at the transmit from the Pi again, which is the orange wire. Huh. Those little bouncy bits were a little interesting. There's our pulse. That does look faster. It still looks electrically pretty weird. Like that multi-level pulse is kind of strange. I don't know whether that's like another circuit contributing to that or like crosstalk from the other polarity. There's a lot more of the switching transients without the resistor load. Well, let's see if we can do that packet generation some more with that ARP ping. Alright, it doesn't say running this time. So one option here would be, I'm going to test a couple things before making any changes, but it might be that it needs a pull-up resistor, just not something quite so low value. Let's see if the link pulses look okay on the other side of the capacitors. Kinda. Yeah. The capacitor might be doing more harm than good in this particular situation. I don't know about that. Let's see if we can do that loop back again, since I don't think we can even send packets if it doesn't think there's a link. Doesn't have that running flag. So let's try just... Ooh, I need to glue these pins in. I hate it when I pull the headers and out and the wires, or I push them in and the pins and the headers don't stay together. End up needing a little bit of glue or something. So, anyway, wire or capacitor? Let's try capacitor to be on the safe side. Let's try capacitively coupling a loop back into this and see if I can make that work. Yeah, the pulses are still ugly. I think what I'm seeing is that, I'm just operating this driver circuit way outside of what it was designed for, and I don't know enough about how an Ethernet PHY is built internally to know what particular aspect of it I'm stressing right now. But I expect it has something to do with, the output stage probably has different transistor pairs that are designed to handle different parts of the, I would expect that maybe they would divide the problem into the very beginning of the pulse or maybe later in the pulse, and so maybe I'm seeing something like that where it isn't well matched anymore. I'm imagining a crossover in a stereo speaker, and then I'm changing the size of the tweeter or something, and at some point the crossover just starts to not actually be helpful. So I think what I'm doing here, let's take that off the clock right now. I'm just going to put the scope probe on. Well, I'm going to start with just the positive maybe, but I want to do another one of those differential setups so I can look at just what the receiver is theoretically seeing. What was that reference to? It's not super useful yet. Am I even seeing link pulses? I think I need to back up a step. I am not seeing the link test pulses, so let's make sure that I'm even getting those. I feel like I'm going down some kind of big checklist, and if I kind of forget where I am, I have to back up to some kind of save point. So orange, transmit. Let's just have it be open circuit right now. Let's see what it looks like trying to drive an open circuit. So that one, let's DC couple this because I care about voltage. 0 volts or so there. And there. Okay, yeah, maybe it's possible these are just open drain. Maybe that's what I'm seeing. And I might have been seeing something else with like the open drain driver kind of pulling against this like weird capacitive load that I've given it, but maybe this does just need less severe pull-up resistor. So I think I need to bring some more power wires over there. Also starting to feel like I could really use a bite to eat. Hey, Tuco. Oh, maybe I'll catch up with the chat because it looks like there's a lot of good suggestions here. So one suggestion is that maybe maybe C10 needs to be adjusted. Which one is C10? Oh yeah. So I don't think that's even necessarily relevant right now, since right now I'm just concentrating on the transmit side, which is just R4 and R3 and pretty much nothing else. It's looking right now like these are just like, if not single-ended drivers, something close to it. So this is just pulling TP out plus to ground or pulling TP out minus to ground. That's fine. My first inclination is to put a larger value resistor in here. I'm also wondering if it might be worth buffering this somehow. Like perhaps, like if it is just like some awful single-ended driver that works great when I've got this transformer, but is bad for driving a cable directly, then maybe what I do is I replace R3 and R4 with, I don't know, like 1K or something, or like 220, or maybe I even keep it as, 49, maybe it's fine, and then just immediately buffer that instead of trying to send it any distance. Yeah, and then the other thing is I would totally just bring out 3.3 volts to the breadboard and start putting some resistors in there. I think that is probably the next step. I'm just realizing that I need to solder some more wires to get a solid 3.3 volts close to here, and probably decouple it a bit. And I think I want to eat dinner before doing that, so I think this might be approaching a good stream wrap-up time. So let's try to summarize what's been going on here. So we ran into some of the electrical problems with just underclocking this and trying to still make use of the output of this like drastically underclocked 10 base T over 24 adapter now. And we're hitting some problems that seem to be related to the phi. Capacitive coupling does work, but not very well, at least so far. So with the capacitive coupling and the unmodified transmitter, I'm getting some packets through, but they just don't look very good. And so the receiver, I imagine, is having trouble decoding them. And I don't see the microcontroller on the other end trying to transmit anything yet, so we haven't even tested that side of the circuit yet. It's also possible that some of this would be easier if I underclocked this less, which is certainly an option. I'm trying to get it away with as much underclock as I can. 5 megahertz seemed pretty tantalizing. as a target instead of 120 megahertz, but we'll see what we can do given the available constraints. Hey, Tuco. I'm going to see if Tuco is into a little bit of playing before I have to get my sandwich. It's also possible that I could eat my sandwich while Tuco plays, and then we could go back to this. So maybe I'll let Tuco drive this next part of the stream and see if he feels like playing. Hey, Tuco. Do you have a bolt? Oh, he's so interested, but also skeptical. Tuco. All right, well, it seems like both Tuco and I are in the mood for some dinner and slightly antisocial time. So maybe this is a good point to wrap up the current stream. But we'll be back soon, I'm sure. Meow. Do you want to play, Tuco, or do you want to eat? I can't quite tell right now. Well, there's that. He's like slightly in a mood to play. All right. Well, I think it's dinner time in this household. See you on the next stream, everyone. Meow. I know, Tuco.